I'll check and let you know.
How many questions will be there, sir, for the exam?
Around 17 to 18, I think, or 15 to 16 questions will be there, including some sub questions. So that, sorry, excluding the sub questions.
Excluding the sub questions.
Yeah,
Okay.
yeah, yeah, yeah. Okay, weightage, right? So just give me a minute. Check. My screen is not visible, right?
So please share it, sir. We will see it also.
What? What should I share?
Share your screen, sir. We can also see and see the weightage by ourselves.
You can see the weightage you're saying. Okay.
He's joking, sir.
Yeah, I understand.
Good evening, sir.
Yeah, good evening. Just give me a minute. I will just let you know what is.
By the way, can I know your email, sir?
Yeah,
It
yeah.
is
Mayur at the rate study .iitm.ac.in. I will
Mayur at
paste.
the rate.
I will paste it in the chat box.
Okay, okay.
Yeah. Okay. I think okay. So the weightage is like 50-50. Like around, you can think of like this: 50% for week 1 to 8 and 50% for uh, week 9 to 12. So more weightage is to last 4 weeks, and like 50% weightage. So out of your whatever scores will be there, 50% marks will be coming from week 1 to 8. So week 1 to 8 also are equally important, right? So study team.in. Okay, this is my email ID. You can check it in the chat box. You can mail me over there. I'll check, or you can mail me, or you can message me. Fine. See, that is what. So I think all are the important topics. See, the here it's not. We cannot see. It's not like it is mathematical course, but still it is not like it is like we have like 12 weeks. But what are exactly in there in 12 weeks is, let us say, I can say 10 to 12 algorithms, right? Or 10 to 11 algorithms, right? For PCA algorithms are there for, or maybe you can unsupervised. We saw two algorithms, or I think two or three, yeah, two algorithms, right? GMM, possibly clustering, or maybe clustering and PCA, right? And clustering also we have seen two. So these three, let us say, three algorithms there. Then regression, and then classification. We have seen so many algorithms, right? So based on that, so the important thing is to know the processes, to know algorithms, why we are actually doing what. That is important. So here it is not like I cannot say that which topic is very much important than the other. The questions will be there on most of the topics, like all the topics you can think of. The questions will be there, but the questions will not be like very much numerical. I'll say there are numerical questions, but uh, mostly the questions will be like based on your understanding, right? So if you understand about what is kernel PCA, what does it do, the questions will be based on your understanding. Why? So what does kernel PCA do is, let us say, it tries to find out the relations in the transform space, right? So like that, what does regression do? What does it do? It will try to minimize the error, or that is like squared error loss will be there. and the error between what? Error between the labels and the predicted values, right? So and again, we why we are doing that, right? And why this normal, why we are taking the square error loss, right? Why not the other? So those things you should know. So basically, mostly it is like what you know from those algorithms, why we have chosen for those algorithms. That is more important than. So there are not like any particular topic which I can tell you that okay, this is the important topic. I'll say that all are the important topics. At least go through the algorithms, what are there. Go through the search notes. I think those are the important ones. Wherever you feel difficulty in understanding it, right? Then you just go and watch that part of the lecture. That I'll suggest. Fine. So there are no like I cannot say that okay, this is the very important topic and the questions will be coming from there. It's not like that. I think if you see the previous year questions also, you will find out the same thing, right? Almost all the topics, the questions will be coming, right? So yeah, but you can see that numerical questions will be lesser, and the theoretical will be there. But numerical also will have to do. So yeah, maybe we'll start it in 2 minutes. Just give me 2 minutes. I'll just set up this part and then we start.
Sir, you raised the question about squared error in regression. You talked about the importance of knowing the importance of this squared error. Uh, I I mean, hello, hello,
We can hear you with that.
hello. So, is there a specific reason why we use the squared error, or I don't remember that? Does anybody know why exactly we use that squared error?
I think one reason is that it helps to give error regardless of the direction of the error. So we don't end up adding, plus 2 and minus 2 to make 0. That's something that square helps with. Regarding why we use square and not say the mean, also the absolute value of the error, I think it has to do with something about how the modulus function is not differentiable, but the square
Yes, that's
is.
what I also thought. So, is
Is
that
that
the
correct?
reason?
I do think so. I'm not sure though. Maybe someone else can take it.
Yes, differentiability is one of the factor, I think.
Square error is convex, so yeah, differentiability.
Yes, yes, that is another reason. It's a convex,
What
and
does convex have to do
we
anything?
can find the minimum of that, right?
It means every local minima will be global minima, so it's easier to get the optimum for a convex.
But will that also not be true with the modulus function? I mean, it's not differential, but the minimum of the modulus is both a local and a global minimum.
It helps in the optimization. I mean, the KKT conditions and all that.
What is
If you
this?
don't square it, that also is a convex function, right? If it is a linear form, that is also a convex function.
Then it's modulus, no?
It is
The
not
distance is
differentiable.
it's a differentiable, right? Okay.
On another note, does anyone, secondly, if someone knows this, what is the difference between kernel and kernel PC and PCHS status? Or we shall pick we shall do it later.
Yeah, okay. Sorry. Yeah, somebody was saying something. I think Siddharth was saying something. You guys were talking about some
Yes, you are
linear
talking
function.
about the squared error we use in regression, sir.
Hmm.
And we should know the importance of the squared error as compared to the other errors. So, I think I forgot the exact reason why we use the squared error only. Is it because it's a convex function and it has a minima and it
No,
is
no, no, no. It
differentiable?
is. It is not like that. See, again. Okay. First thing is, we wanted to minimize the error, right? That was our goal,
Right,
right? In general,
right, right.
the error which we can choose either you can. So if you wanted to minimize, you don't want that error to be negative side, right? That is first
Yes.
condition, right? why
Yes.
why what will happen then you will have like entire range of values, right? Minus infinity to plus infinity, if you allow negative errors to be there, correct? Again, the
Yes.
errors are actually not negative, right? It is just you just think about it like it is the how the true value is away from the, or how the predicted value is away from the. So just these are the deviations, one thing. So that means you wanted all these deviations to be counted as positive instead of the negative thing, right?
Yes.
So there will be maybe the broader level, if you think of that, there may be two choices. One choice will be your squared error loss, because that will make your all the however you take the difference between the predicted value and the actual label, that difference will always be positive, right? And then if you minimize it, I think that will give you the answer. Another second thing is you can actually use the absolute value. So always you take the absolute difference between the predicted value and the actual label, right? That also is a choice. But generally we go for squared error, and that we've seen that why that is a good choice, not a good choice, or yeah, why that is a good choice is because if you remember that part where sir has said like y given x, so you just try to find out the uh, uh, where you use the maximum likelihood, right? So given the data, how the labels are generated, if you think about that way, and if you take the maximum likelihood estimator, in that case, we are assuming that y equals to, let's say, w transpose x plus epsilon. Epsilon will be the error, and that error, we are assuming that it is a Gaussian error. And why now this is going to be, if you assume the
Noise,
error,
noise, you mean the
yeah,
noise epsilon.
yeah, noise or the error, right? Basically it's noise or error, the same thing. So if we are assuming that Gaussian noise or Gaussian error, and why that is a good choice to have is because if you have that Gaussian noise, right, what we have seen from your understanding from stats and all, right? So generally in our real life examples, the errors are actually distributed uh, according to normal distributions, right? So normal distribution will be a good choice to have, and if you uh, do that way, right, given the data how the labels are generated, if you try to see that, and if you found out the solution which we have got for the w star, or that optimal solution, is exactly equal to the solution we get by optimizing the squared error, right? If you assume the Laplacian loss, then you will get the solution for the optimal solution will be like the Laplacian noise. Sorry, not Laplacian. So if it is a Laplacian noise, if you consider, then the solution you will get will be a absolute deviation, right? So these were the things, right? So I think, and then the choice will be of, if you are going to assume that the noise is a Gaussian noise, in that case your error is actually a squared error loss. If you assume the Laplacian noise, the error will be the uh, which one,
Modulus.
modulus, right? So that was the case, and we have proved that. Okay, so if you assume this way, then you will get the squared error. So either you can find out from the training data, find out all the deviation and try to minimize that error and find out the w, or what you can do is, given the data, try to generate the labels, right? And use the maximum likelihood estimator to find out that parameter, right? I hope you are understanding what I'm trying to say, or maybe we'll see that, like we'll quickly revise that part. This is week 5, right? Week 5.
Yes, sir, I think.
Yeah, supervised learning we've started. So yeah, this was the case, right? So linear, I think, I hope all of you understand linear is why the choice. We just see for linear, and we see that okay, we just find out, we wanted to find out this error, right? So you can actually do the squared error loss, or you can do the absolute deviations. You don't want the negative ones. And then I think went through, okay, this was the case. We have found out this w star, right? What was the w star? X6 transpose inverse or pseudo inverse xy. And the same thing if you go the other way, which is this one. Okay, not this one also. This is the kernel regression, probabilistic view. So y given x, so given the data, how the labels are generated. In this case, if you assume this epsilon, which is because you know, right, so it is w transpose x will be the ideal line, and w is unknown here. And if you are assuming that the noise is Gaussian noise, or why we are assuming this, because most general in real life scenarios, we assume any distribution to be a Gaussian distribution, and by adding this here, what will be the distribution of y given x?
That will
Normal
also be normal.
Normal
W
with mean
Mean W transpose X,
transpose X.
and variance
sigma
sigma
square.
square,
Sigma is good.
right? So that means in general what we are saying, that this distribution is a normal distribution, right? Correct. All the labels are generated according to a normal distribution given the set of data points. That is the meaning of it, right?
Yes, sir.
Okay. And then if you use that approach and find out what is that w, right, given this, and we again found out this solution. Fine. So maximum likelihood estimator, assuming zero mean Gaussian noise, is same as that of linear regression with squared error.
Right.
So that's why uh, the choice is the good choice.
Squared error
Squared
is a
error is the
good choice.
choice, right? Okay. So let me start with this part. Uh, Maybe I'll write down something, so I think that will be easier for you to again follow up, or I can just go through here and maybe see some examples. That also is fine. It's up to you. Uh, Writing will take time, but let us see. We will see like what are the important points here, right? So, okay. Shall we proceed now? Then it's fine. Any other questions from previous weeks?
No, sir.
So in week 9, we majorly are dealing with two algorithms, which is one is perceptron and another one is
Logistic regression.
right logistic regression. Yeah, and then in subsequent weeks we have seen the support vector machine, which is actually based on this only, right, perceptron algorithm. So okay, these both are the algorithms for what? Let us say, okay, in this case we are
Linearly separable.
Classification.
or binary
Binary
classification.
classification. Binary
Right.
classification.
Actually, it can logistic regression also we can use for multi or more than two right classes if there are there. Multi-class classification also we can use it, but uh, since we are actually for looking for this mathematical arguments, right? So here we are actually looking only for uh, these two classes, right? Okay, so right. So where to start here is, let's say, so I wanted to check this minute. I'll just see that maybe here. Okay, so perceptron is what, like, what is your understanding of perceptron?
Applicable to linearly separable data
Yeah,
sets.
so we have some assumptions, right, for perceptron. Perceptron is, okay, I'll just go through like quickly. So perceptron is applicable to applicable sorry
Sir, your screen is not
oh,
visible.
okay, okay, sorry.
Also, sir, could you explain what a linearly separable data set is?
Yeah, sure, sure. So linearly separable is basically the data set which perfectly classify the uh, the data points. Okay, we'll try to see that. So first thing is, the assumption we make is for perceptron. For perceptron, the assumption is the data is linearly separable. Okay. So what does that mean by, right? So what is the meaning of linearly separable data that we wanted to see? So the mathematically I'll try to show you, and then we can see it for uh, like by using the graphs also. So mathematically, what is it? So we wanted to find a w, or we are saying that there is exists some w, right? There exists some w in d dimensions such that sine of w transpose x, what is w in our dimension is basically it's a vector, right? And or you can, yeah, and what is w transpose x? Say equal to yi for all I. This is mathematical thing. So what we are saying is the what is this thing?
Number, scalar,
Number is fine, but what exactly is this? Like, yeah, it's a
scalar, sir.
It's a line.
yeah, it is a line. So w is
It's a
basically
line.
w transpose xi is basically you can think of it's a line, right? Or you can think of it as a perpendicular line to w.
W, yes.
So when I say perpendicular, then it should be w transpose x equal to 0, right? Generally,
Yes.
see, why I'm trying to say is, let's say you have a data like this. Sorry, this is not colored. So suppose you have data set here like this, right? And I'm okay. Initially, I'm just saying that okay, these are the data points. Okay, and these are some data points here. Okay, so I'll just name some few of the data points. So it is, let's say it is x1. This data is it is x2, right? This is, let's say, x4, and this is x5, something like that. Or you can think of this as x6 and x7. Fine, not required, but yeah, just try to understand that. I'm saying that there is a vector w, and when I say vector w, what does it mean? It should pass through origin, right?
Yes.
Right.
Yes, sir.
So let us say there is this vector w. It can be like this, or like whatever length, right? What length is, length doesn't matter here. I'm saying that this is vector w. Okay. Uh, this is what is
X1.
this is a vector x1, right?
Yes,
Basically
sir.
the data point is nothing but a vector, right, in that dimensions, let's say d dimensions. So is it fine?
So just to clarify, so if taking a practical example, maybe if say we're building like an email spam classifier, and X1 X is some characteristics. So let's say the suspiciousness of the sender,
Hmm.
and so if that we put a score on that and we plot those scores somehow, and W is how the vector joining the origin and that data point X.
Same thing, right?
Is that
What is
correct,
like,
sir?
yeah, that is fine, right? So you
Yes, sir.
have let's say you have some mails or whatever thing is there, actually you are thinking them as a data point only, right? We are actually
Yes, sir.
vectorizing them, right? Anyway,
Yes, sir.
so think of this as a data point, right? So how will you say that in practically also? Let us say I will get some money, right? So if you have that kind of thing, we already are vectorizing how, and we have learned it, right? So you have a dictionary, you just give some numbers to it, right? So you have some dictionary and you say that okay, from the dictionary, let's say you have 1000 words or 10,000 words, what you can now, you have this 10,000 words here, right, in the dictionary. And what will be the x1 then according to this? So let's say every zeros will be there. Whenever I will pop up, it will be 1. Then it will go again like all 0 0 zeros. Then you will have some wherever will is there, and again you have zeros, some, right, like that. This will be your vector, and it will be in 10,000 dimensions, suppose, because the length of the
This will
dictionary
be
is that.
W, sir. Is that correct?
This is not W.
Vector?
This is x1, right? All the data points, right? So this is a male, right? Is x1 is a male. I'm just converted into this vector, right? You have bunch of males, and let us say y1 is a label corresponding to it. So plus one is, let's say, spam and non-spam. Now it's non-spam, so I'll just put it as -1. Suppose x2 is your some male, like you, okay, uh, if you, let's say, if you scratch this lottery or something, you'll get money, right? Get some money like that, right? So money is that there. It will be having, we can actually encode into this, right? Again, some, and the corresponding label will be what then? +1, right? So you can, based on whatever numbers are there, you can actually plot it in the dimensions, right? Like that. So think of like that. This will be the data points. W is a vector which I don't know actually, right? As this point, at this moment, I don't know the W. W can be anything, right? Right? Any W, but I wanted that W. If I uh, if I multiply, or if I take a dot product of this W and x1, uh, and if I take the sign of it, right, that that sign should be equal to what? The
Plus
label.
one.
Label,
Label.
right? Not +1, label, right? In this case, suppose if I have this x1 vector, and if I have some W, that W, if I take a dot product, W will be some vector, right? It can be anything that we wanted to find out anyway. That is our goal anyway. But let us say that W, if I take, so what is W transpose x equal to 0?
Perpendicular to W.
Right? So W will be what? So like all the x's are there here, and if I take the uh, the dot product with all of them, it will be what? Then W transpose x will be 0. So that will be a line, right? And that line will be passing through,
Origin.
right?
Origin.
Right. Why it is passing through origin? Because W also originated from origin, and this line now, right? This is what? This line is W
W
transpose
transpose
x.
W
X.
transpose X.
Because we know that when W transpose x equal to 0, that line is perpendicular to the original
W.
W, right?
W.
So you have all the data points, and you are taking the dot product with that W, and then you find out this line. Now, if this line is able to perfectly classify all the points, right? So what does that mean? All the red points are, let's say, these are the plus classes, positive class, and these are negative class. Uh, if if it is if this line is perfectly able to classify that, then that line will be a good line. So how many lines will be there, or how many W's are there which can
Many.
actually, so there will
Many
be
are
a lot of, right?
infinite.
Right. So yeah, so many W's you can find it out, like this W is also fine, this W is fine, this W is fine, like any vector in this, let's say in this circle also, right? That will perfectly able to. But whatever the data set you are looking at here, that is a linearly separated data set. And which one is not linearly separated? If I wanted to say that, let us say if any data point here, this data point which is having, because uh, our training, or whenever you get a data, you will have the labels corresponding to it, right? So that means we already know what is the label corresponding to that data. That's where actually supervised learning is differentiated from the unsupervised learning, right? So if you think of, let us say you have some data points here, right, which are negatively labeled, and some data points here which are positively positively labeled, right? But if any of this line, right, or any of this W, are they able to correctly classify these two data points?
No, no.
No, right? Because this, according to this line W, whatever data points which are on this side, they are what? Positive,
Positive.
right? And whichever data points which are on this line, they all are negative.
Negative.
So these data points, even though in so we know, right? We know that already these labels are negatives, right? How we know that? We have the sense, right? Anyway, we know that okay, this is
That
a
would be
spam,
training data, right? These data.
right? Yeah. So during training, we know that already. So, but the prediction of this, because of this line, will be what? For this data point, the prediction will be negative. For this
Negative.
also, it will be negative, and for these two are positive. So, how many data points we are like incorrectly classified?
4.
4. And one more thing is class. Okay, that misclassification is a different thing. But now, if these data points are there, will we get the correct W which can classify or which will be able to satisfy this condition? Now,
No,
no, right? Because
no.
any W now, if you take any W, it will not be able to correctly classify these 4 data points, right? It will never be able to do that, right? And here actually, what happens then? Then here the linear separability condition fails, right? Is that correct?
Yes, sir, that makes
Yes.
sense.
So, but okay, but we need to develop some algorithms, right? So we are not allowing this kind of data sets according to the perceptron. What we are saying that we just only talk about those data sets which are linearly separable, right? Linearly separable means the perfectly separated, right? So all the positive data points will be on one side, and all the negative data points are on the other side, right? So with this condition, linearly separability assumption, what we are saying that what is the perceptron algorithm? You have some input. What is the input? All the
Data
data
point.
and their corresponding labels, right? So this pairs will be there. So x2, y2 up to, let's say you have n examples in your training. We have this data sets. Each of xi will be in
RD.
d dimensions, right? Each of yi will be
0, 1.
positive and negative,
Okay.
right? So we are thinking about the positive class or negative class. Then what is the, and we, okay, now we initiate with some w, because we do not know the w, right? That is our goal. So initialization will be with some w, which is, let us start with the zero vector in d dimensions. So how this will look like? Okay, all the
D
zero,
times 0. D
yeah.
times 0.
So it will be a vector of
Matrix.
vector. It will not be a matrix, right?
Yes. D times 0.
It will be like this: 0, 0, 0 up to some zeros, and this is d cross 1. Right? It's a vector, right? Okay, and then the update rule is what?
W1 equal to
Yeah,
W0.
first of all, pick the pair from the data set, right? So in this algorithm, one thing is very important, which is what?
Order of the
Order.
pairs.
So which data point you are selecting, or from where you are going through, that will affect your w's, right? The choice of w, right? So pick any pair from this data set, so let us say if I started with x1 y1, and if I go through this algorithm, let's say from left to right, my w optimal, or my w when I get the convergence, it might be different if I start with x and yn, and from right to left, right? So this will always be important scenario. We'll see why that is the case. Let us say pick XIYY pair from the data set. Now what is the algorithm says? If,
Correctly classified, then nothing to do.
yeah, if sign of correctly classified means if sign of WT transpose XI
X.
X
is
equal to
equal to
Y.
YI,
YI.
if it is there, then
Nothing to do.
do nothing, right? And else
If sign is not equal to ii, then use
W
the
WT
trans-
plus 1 is WT.
transpose, or okay, then or equal to
WT
WT
plus
plus
XIYI.
xi yi. So you are adding that xi yi there, right? And that is your update rule, right? This is the update rule. This is your update rule, right? This is the algorithm you will have to understand. Okay. So and here, what is happening here? Yi will have this plus one minus one class, right? So wherever you do the mistake, you'll get that point, and you do this procedure till what?
all the points are classified
Yeah,
correctly.
that means it will be like until convergence, right? So let us see one example for this. Let us a numerical example, and we'll try to understand. That's fine. You understand this algorithm? The simplest one. I hope you understand this part. Uh,
Yes,
Yes,
sir.
sir. So just to clarify, as you mentioned, the order of which xi yi we start with
yeah.
will change the w that we get as our final answer.
Yes, yes.
Right.
Because
So
so
yes, sir.
so
So
final answer.
which one
Okay.
should we start with in general? Is
No,
there
we
any?
should start with this. This is the initialization, right? Okay. Which point you are saying we can
So
start with?
you mentioned, I think you mentioned that the pair
Pair.
that we select,
Yeah,
that is
there is
also important
no.
because it affects w, right?
Yeah, so it is not important as such. What I'm saying is you might get different W, right? So, but that is not the wrong W. That will also be a correct W. So there is no like one solution that okay, this is the W where or this is the final W. There is no such kind of thing. You understand? Okay,
Okay.
I'll try to show you something,
Sure.
and that will be the better way to do that.
We can even start W0 not equal to 0, right? That also is possible. No? W0, even if it is not equal to 0 vector, then also it's okay. No? We can use any starting point also.
Yeah, that is so all of so there are two things here. Either so this is also important, right? If you start with zero vector, you will get something else. If you start with some other vector, that also will give you the something else, right? That is another part. What are you trying to say is uh, so there is no like, I'm not saying that okay, this is the correct answer. It's not like that, right? So order is very important. I'll tell you
There can be infinitely correct answers, infinitely many correct answers, right? So
but
any
generally
one,
it is not like that, but yeah, but you can say that theoretically, yes, right?
because there are many lines which are
Yeah,
separating the point.
yeah, separating the data set, right?
Sir,
Yeah.
in one of the formula book that was given in the MLT course FAQs,
Mm.
it said that Perceptron algorithm makes predictions using the rule that is y cap is equal to 1 if W transpose X is greater than or equal to 0. So does that mean that we can,
No, your voice is breaking. No,
are
sorry,
we
sorry.
like checking the signs? Hello?
Yeah, I think I didn't hear you properly. Anyone was able to hear it? No, right?
Hello?
Yeah, yeah. Now, yeah. Yes, tell me.
Yes, sir. Actually, in one of the MLT course FAQs,
Hmm.
that was given that Perceptron algorithm makes predictions using the following rule. That is like if W transpose X is greater than or equal to 0, then it is classified as 1. So are we using the same thing
Yeah,
here
yeah,
to
yeah,
check the sign?
yeah. Correct.
Okay,
That's
sir.
correct.
Because you didn't mention it, so I got a doubt. Okay, sir.
I think it is mentioned. No, if the sign of this thing is equal to yi, what does it mean? Yi is taking what values? Plus one and minus
Plus
one.
one or minus one.
And sign
Okay.
of, let's say if you have W transpose X is minus 5. What is the sign of minus 5? Minus 1, right?
Minus.
If it is plus
Okay.
5, then it is plus 1, right? That is what it is the meaning.
Okay.
Okay. Yeah.
Okay.
So how this data point, where are these data points? Minus 1 plus 1 will be somewhere here.
First, second quadrant. Yes.
uh, 1 will be
Fourth.
somewhere here, and 1 minus 2 will be somewhere here, right?
Yes.
So are these data points linearly separable? Yes, right? So
Yes,
Yes, sir.
you can think about this line. This is like, okay, y-axis itself is able to, or x2 axis, right? Here in this case we are saying that it is x1 and it is x2. So x2 axis basically is giving me, there are other lines too. So this is one of the lines, right? One of the potential candidates. What else is there? Maybe I can choose, okay, for this, okay, sorry, not this one. Your w will be this one, right? Okay, this is one of the candidates, right? So then the x2 will be separating this. Then what else is there? uh,
Any you can draw a deviated
so
line
yeah,
also.
suppose if I chose this one, I don't know, okay, somewhere like this, let us say, right? And that means this w perpendicular to this can be the line, right? So that means we have more than one choices, is that correct? But which one we are and getting in, like, or getting it, we'll have to see that. So what is the update rule now? So let us say if I start with this point from left to right, what should I do now? uh, let's say I initialize with w not equal to 0, 0 vector in r2, or maybe I'll just write it down like this, 0 0. uh, okay, what will be w1 then? W1 will be, or w1 will be
0 0 plus
0 0 0 minus 0 0 minus
0 0 plus, right?
plus xy
Or yeah, x1, right? X1
1
y
minus
y1.
1 into
yi,
minus
right?
1.
My into minus one.
Right,
Into
because of
minus one.
minus
That's
1.
why I said.
So that means I'll get
1 minus 1.
0 0 plus 1 minus 1, which is 1 minus
1
1.
minus 1.
So and okay, before going to there, I'll have to check whether, have you checked here whether it is correctly classifying or not?
No, it is
So
not
It's
correctly
not correctly
classified.
so
classified.
W transpose X equal to, we'll have to find
0
out this, right? So W transpose X equal to 0.
0
And we said that, like, let us say there is a
plus
rule.
1
So whenever W transpose Xi is equal
more
to
than
0,
equal to
yeah, greater than or equal to 0, then in that case we assume it as plus 1,
plus 1.
right? Or I'll say that sign of this thing should be plus 1. So that means it was not correctly classified.
Classical.
Okay, so now this is the updated vector. For the second point, what I should do now? W1. First of all, I will have to check. So W1 transpose X2, right? What is
So
W?
will x1 will surely be correctly classified
Right.
if
That is not sure also, right? We'll have to check that, but we cannot stop there, right? The only
okay.
thing we are sure about that we are actually going into the correct direction, right?
So we don't have to recheck for x1 now.
No, no, no. You can't add like immediately. You'll have to iterate. No, this is iteration algorithm, right? You
So
can't.
just to confirm then, sir, just to confirm. So we pick up first initial some xi yi pair, and then check it with w0. If not, updated accordingly.
Yeah.
And then we move on to the next xi yi,
Yes.
and then check it with w1.
Yeah.
And if it does not fit, then we move on to the next xi yi, check it with w2, and so on and so forth. Right.
Correct. Correct.
If it does work, however, sir, we'll come to that. Maybe what do we do? If say we check x2 y2 with w1 and it works and it classifies correctly,
Then
then
it's
we check
done,
it
right?
with
No, no. We'll have to stop there. No. Okay. We'll see through. I don't understand. What, let's say just check it here. So 1 minus 1, and what is x2 here? 1 1, right? So what is it? 1
0 0
0. So again, it gives me, so sine of W1 transpose x2 is plus 1, right? And y2 is equal to plus 1.
plus 1.
So that means it is correctly
Correctly
classified. So no mistake, right? Okay, I'll say that no mistake here, right? No mistake. That means we don't need to update W1, right?
Yes, sir.
So we'll use that same W1 transpose x3.
3.
So what that?
Sir, we need to even check it for x1, right?
Where? Here. Okay, yeah,
Yes.
I think we should do. Okay, let us see, but I think it will classify right now for this. Let us see what it should be. If you don't check also, it's not a problem, because again you can go back to the first and I think you can modify it. That's because that is what I'm trying to say, that it's not the problem there.
Every time we get a new W, should we start from the first vector, or
No,
we
you
have
can
to
start from the next one
Okay, okay, okay.
generally, right? So you don't have to check it again here, that whether it is correctly classifying or not. But we know that we are, for that data point, at least we are going into the correct direction. Is that correct?
Yes, sir.
But if you wanted to check, like, you can like quickly check here for first data point. I think it is going to be correctly classifying, but let's see. And it is going to give me again, it is minus 1 minus 2, so the sign of that will be negative.
Minus.
It is again anyway correctly classified. Let us see for the third one.
Sir, sign of 0 you have taken +1.
Yeah, because that is what we have said, no?
Okay.
Sign of this will be +1 and W transpose X is less than 0, it will be -1. That is the
Okay, sir.
so what is x3? X3 is 1 minus 2. All right. So 1 minus 2, and then uh,
3.
it will be plus 3. So that means it is again no mistake. Fine.
No, yes, sir, yes, sir.
No mistake, right? So no mistake. That means we have got the convergence, because this W was able to correctly classify all three. And what is that W then?
1
So that,
minus 1.
so this will be the final W, right? 1 minus 1. So let us see from the this side what will happen, right? Okay. So if you start with the, let's say again, I'm starting with the same 0 vector, 0 0, but I will be starting this one from the right to left. So I'll take W0 transpose X3, right? Okay, will that be fine? Again, it is going to give me 0 0 vector, so that means it is going to be
Correctly classified.
classified. Again, if I go for the
X2, again it correctly
it will
classified.
also correctly classify. So now again we'll get what, which one?
X1, which is
The
incorrectly
same.
classified.
Yeah, but again I'll get the same answer, right? In this case,
Yes, sir, yes, sir.
I'm not getting a different one. That is again another case of it, right? If you understand what I'm trying to say, this will be the case. But now, instead of that, what I'm trying to do is, let's say I'll add one more point, which is x4, which is let us say, which is uh, here this was 1 minus 1, right? So here I can take off -1 and its y4 will be -1. Is that okay? What happens now, we just see. So you understand what to do now here? Then it is not okay, then we'll have to check for W1 transpose X4, and what that will be then? 1
0, which is
minus 1 and -1 -1, so it will be 0.
0.
So
0.
that is positive. So there is a mistake.
Misclassification.
So if this is a mistake, then what I need to do? So W2 will be W1
W
plus xi yi is
minus
2 minus 1.
so that will be 1 minus 1 plus
1 1.
1 1. And what is it then?
2
2
0.
0.
2 0.
Right. So now 2 0 is there. Then what should I do now? Whether this 2 0 able to correctly classify now? Let us see that also. But okay, generally I have to. I told you again, right? So we generally have to go from go for the next
Sir, that point was 1 minus 1.
-1, right? The fourth one,
Oh, okay.
right? I've just taken one more point here, right?
Okay, sir.
So that is somewhere here.
So again, we have to go from x1, x2, x3.
Yeah, but okay, let us see here. First of all, generally I'll have to go, but yeah. I'm just saying that we'll check it here itself what is happening here. So it is -2, that means it is correctly classifying, right?
Yes, sir.
But now again I'll have to go to the first point,
X1.
because
X1.
now there is a update, right, happened. Now we'll have to check again for first point, which was, let's say it is 2
minus
0
1 1.
minus 1 1, yeah. So what is it now?
-2.
Minus 2.
So that is
Correctly classifies.
correctly classifies, no mistake. And next one will be 2 0, and what is the next point? This is W2 transpose x1. This is W2 transpose x2. What is x2? 1 1,
1
right?
1.
So 1 1. Is it correctly classifying?
Yes, sir.
Yes. Then W3 transpose x2, which is, let's say, 2 0, and here
2 transpose x3 or
W2 transpose X3.
x3 will be 1 2, and yeah, it is again
Correctly
classifying
classified.
correctly. And W4, now see, this is where sorry, here it is W2 transpose. So W2 transpose x4, again it's going to be like, right? So
Correctly
here
classifies.
yeah, here we will check actually, but we already have saw that like it is getting me the correct answer. So that means here we'll have to stop. But now if I do different way, right? If I start from the fourth data point, will that be the same answer or will that be a different? That we'll have to see. Okay, I'm not sure whether this gives me the correct same answer or not, but let us try. uh, what will happen in that case, right? So what will be W4 okay, W0 transpose x4. So it will be 0 0,
0.
and then here it is -1 -1, which is 0. So there is a mistake right here.
Yes, sir.
So then what will be my W1 transpose x, W1 transpose, sorry, not W1, will be W0 plus -1, right? And what is it getting me?
1 1.
1 1, is it correct? Okay.
Yes,
What
sir.
will happen if I then I'll have to use the W1 for uh, the next data
X1.
point, 3
X1.
3 3,
Okay.
right? So W1 transpose x3, so it will be 1 1, and what is x3? X3 is 1 2, right? Hmm? Right, okay, just check it here. I'm going from here to here, right? So now y x4, then x3, then x2, and then x1. So if I so x3 is 1
1 -2. 1 -2, I think.
1 -2, and uh, that will be
-1.
-1. So is there a mistake?
Yes,
Yes.
sir.
So that mistake is there. That means I need to update it, and that updation will be W2 will be equal to 1 1 plus 1 -2.
It is 1 and 2. W3.
It will be
X3 is 1 and 2.
1 and 2 or 1 1 -2.
1 -2, sir. You have written there.
Yeah, 1
1
-2. Right?
minus.
Oh, I think 1 -2, right? Correct now. So what is the problem now? Oh, here I think I did,
Here you have taken
but it's
my.
okay. Yeah, anyway,
It
that is
doesn't matter.
yeah, because it is multiplied with 0, right? Yeah, fine. So this is actually 1 -2, right? In the fourth quadrant. This point was in the fourth quadrant, right? So what will be the answer here then?
2 minus 1.
2 minus 1. So now this is update. This update has happened already. So I'll need to go further, and with that update, W2 transpose. What is that then?
X2.
X2. So
1 1.
2 minus 1, and x2 is
1 1.
okay. 1 1. Okay,
It's 1.
and that is how much?
1.
1. So no mistake,
Yes, sir.
right? No mistake. That means we are using that W again for next
X1.
W transpose x1, which is 2 minus 1. And what is the x1 point? I think it is minus 1 1, right? In the second quadrant it was there. So this is how much? -3.
-1. Yes, sir.
No mistake again, right? It's correctly classifying. So x4 again, I think we'll have to check, but I think that will also give me correct classification. So 2 minus 1, and what was that?
-1, -1.
So 1 minus 1. So I think, yeah, this is again minus anyway, right? So minus 2 or
-1.
minus 1, right?
Minus 2
-1.
plus, yeah, minus 1.
There is also no mistake, right? So we have converged to which vector now here? W2
2
is
-1.
2 minus 1,
2
and in the previous case, what was that? 2 0.
0.
So you understand, right? Now, uh, the order is important where we are actually going. So if you wanted to look where are these vectors lying, 2 0 is where in this diagram? Where is 2 0? This one, right? 2 0 vector, right? And
Yes, sir.
and this case, what is it? 2 minus 1. And where is that 2 minus 1 is?
4th quadrant.
I don't know where. Yeah, this will be right. So now this was the line which was separating correctly data point, and maybe this is going to be this line possibly. I'm not sure, but yeah, if I wanted to draw it perpendicular, right? So now both of these solutions are correct, right? So perceptron actually not giving you that ability to correctly classify, okay, or like you will not converge to the same problem, or sorry, not same w, if you like, maybe you can choose any other point, right? Initial, like we can start with this point and you will get maybe different w, right? So initialization and the order of the data points are very important while solving this algorithm, right? That is one of the problems. What else we are getting a problem there? What is the next problem? Yeah, so if you just okay, if anybody wants to say something. Yeah.
How do we update W? I mean, we are finding W1, which W0 is 0, 0. How do we find W?
Update rule, na? Update rule.
So
You have seen this,
first
correct?
put vector into the label, right?
We have to check whether we are doing any mistake or not. If you don't do any mistake, then you don't have to update. If you do mistake, then you'll have to update according to this xi and to yi. xi yi will be that one, which is
Xi is vector and Y is label.
xi is vector, or you can think of the data point, right? Whichever the data point. So I think let us say if in this case when you started with 0 0, right? uh, the mistake was there. So the mistake was there, that means we have added. So this is what is actually x1 point, right? This is x1 and it is corresponding label. This is a label. What is the label here? -1. This is x1. So we are adding that into the initialized vector when the mistake happened. So here the mistake was there, because if you find out w transpose x1, what I'm getting? 0, and that means I'm predicting it as a positive label, right? But actual label is -1. So that's why we need to update my w, and the update is like we'll have to original w plus x1 y1 where the mistake happened, right? W2 sorry, w1 transpose x2, there is no mistake, right? Because it was correctly able to classify the second point, so we don't do anything there. Here also we don't do any mistake. In the fourth point we do one mistake, and what do we do then? This 1 minus 1 we have updated again with this, so it was w1 plus x4 into y4. So what is x4? 1 minus 1, and what is its corresponding label? -1, right? Or here, don't think of this. Is that correct?
X4 is -1, right?
Huh?
X4 is -1, -1.
x4 is a negative point, no? Right?
Right.
Okay, so that was the case. And okay, so what we have understood now. So I'll have to just make it quick, right? Because we have to finish 2 weeks and
Before
we
we
don't
go,
have.
one question I had, very
Yeah.
short. If in the exam, in the end term, we come across a question based on the perceptron algorithm, and then what xi yi do we have to start with? Is there
that
any?
that is given to you, no? It is not like you can't.
Okay,
Yeah,
okay, okay.
it will be told to you, right, from which direction you have to move. That direction will be given to you. Fine. So I hope that is clear. So right, okay, then there is another problem with perceptron algorithm is that the problem was this one. So we'll try to so let us say we have 3 data points, and okay, I'm just taking the same example from the lectures, which is -1/2, right? And there are 2 data points over this line, uh, which is, let's say, is 0 1, and it is having class positive. There is another data point which is say here, which is 0 -1, and it is having -1 class, and this is having positive class, or negative class, sorry. -1, and this is +1, right? So whether this data is linearly separable,
Yes, sir.
right? This data is linearly separable, uh, but the problem happens here is what in the update. Okay, so let us, what is our update rule here? So I'll just quickly do it. What we have to start now? W0, right? Which is
0.
0 0 0 0, right? All right. Then what you should do? We'll have to find out for the first. So W0 transpose x1. Let us say this is my data point x1. Is, this pair is x1. This is, or x1 y1 basically. This is x2 y2. This is x3 y3. Right? What is W transpose x1 equals 0,
0.
and that means it will classify
Correctly
as
classified.
positive, and that is correct classification. So do I need to update? No, I don't
No.
need to update. What about W0 though? So it is not updated, then I'll go for the second point, and then we'll find out W0 transpose x2. What is the answer? Again, it is 0,
0.
Zero,
Correct
and
correctly.
classified.
that will also correctly classify. So here, no mistake. Here also, no mistake. uh, what will happen to W0 transpose x3, and W0
Mistake.
transpose x3 will be 0, and that will classify as positive, but actual label is
Minus 1.
Negative.
-1.
negative. So that means there is a mistake.
Mistake.
And what we know is, if I do the mistake, what should I do?
Update.
The update rule. So we'll have to update W1, and that will be equal to W1 will be equal to
1/2, 1.5.
W0 plus W0
-1 into
1
-1 -2.
into -1.
oh, no, this is not -1/2, this is plus. It's in the second quadrant, right?
Yes, sir.
Into -1. So that gives me, it was 0, right? So
0.
W0 is 0 0. So 0 0 plus this is
1
1.
-1.
Minus
Minus
half.
half.
1 minus half.
Okay, now this is 1 minus half. Okay, what will happen? Now I'll have to check again for
W1.
W1.
X1, X1.
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 Yes, sir.
Correct. So x. So what will be the case then? W1 transpose x1 will be W1 transpose x1 will be okay. What is it?
Minus half.
So it will be 1 minus half, and it is 0 1. So it will be minus half.
Minus half.
So is it giving me correct? No, it is
Incorrect.
wrong. Wrong. So there is a mistake here. Then if I have mistake, then what should I do?
Update rule.
update. So W2 will be equals to 1 minus half, that is W1 plus
Zero
x1 is
one.
0 1, and that will be and into 1, right? Because it is having positive label, so it will be 1 half.
Half.
Now we'll have to see whether W2 transpose, what should I do now?
X2. X2.
X3, X2, X2 will be 1 half, and what is X2? 0 1,
0 minus 1.
0 minus 1. Then it is
1
okay. Sorry, it will not be vector. It will be a sign. Okay, it will be minus half.
half.
So mistake, right?
Half it will be, sir.
Minus, right? This minus sign is there, na?
Oh, yes.
So there is a mistake. So then we'll have to update, which W3 will be 1 by 2 plus 0 minus 1, and that is giving me 1 minus half, right? Now if I just do it again,
It's like a loop.
right? So yeah, so that is the problem happening. So whenever we have such kind of data set here, it will actually so this 0 and half, this 0 and minus half, these are the two things, right? So alternatively we actually end up in getting these two vectors only. We will not be able to converge, right? Why we are not able to converge here? Convergence will happen when
All the points are correctly
correctly
classified.
assessed. So if there are no mistake, then only the class that convergence will happen. So now we'll have to somehow adjust this part, right? Correct? Because this is not, now the perceptron is not getting converged. So what we can do here? We will add the linear separability conditions with
Gamma margin.
yeah. So here it is, linear separability with gamma margin. So what does that mean? We are separating the data with some margin, right? We are not giving away this assumption. So this assumption is there. But what assumption is there? We don't need any outliers, right? We don't need any outliers. The data set is already, because if you think of this data set, whether this data set was linearly separable, yes, right? This was linearly separable.
Yes, sir. But it was too close also. I think that's what you're referring to.
Or you can think of like that we are not end up into, because this data point, these two data points are on the one line, and yeah, so you can think of that they are very close, so we're not able to find out that line which will, so ideally this line would have been the better one, right? Maybe, or somehow like this, some but this is not possible, right? We need to have a line which is uh, or we need to find out that W which actually is going through origin, right? That is also important thing. So what we are adding here is linear separability with sub gamma margin, is that the data point should be somewhat away from the from that line which is able to separate our data points. What does that mean? Is that, let us say this is your x1 x2, right? So let us say you have some data points here, which are, let's say, positive class. These are your, let's say, negative class, and which is the line is able to, which line is separating this data set? Let's say this W, right? This is the line which is actually going to separate my data set, right? But what we are saying is we should have certain distance, right? So let us see here. Okay, I'll just add some here. We are saying that the data points which are on the positive side or the negative side, they should be somewhat away, at least, and that margin is, we are saying that it is gamma margin. Fine. So this is the gamma margin, right? So we are saying that this the separate, whatever the separating line is there, or in higher dimension it will be an hyperplane, right? This will be hyperplane, right? In higher dimensions. we are looking at for only two dimensions here. So because it is x1 x2, I can say it as a line. So this line has to be or whenever the data, this line has to correctly classify those data points which are at least gamma away from the line which is separating the data. Is that correct? So this, what is this line's equation? Is W transpose x equal to 0, and then what is the equation of this line? Is
W
all the
transpose X
x's
equal
such
to
that
gamma.
W transpose x is greater than or
Okay.
equal to gamma.
Line is equal to
Sorry, okay,
gamma.
line is equal to gamma. Okay, fine. Line is equal to gamma. This line is W transpose x equal to minus gamma.
Minus gamma.
Right. So all of these data points, they are at least gamma away from the line which is separating this data point. So in this case, how my equation will look like is that we are going to find out that W such that the W transpose xi into yi should be greater than or
Greater
equal to
than
gamma,
equal to gamma.
right? And gamma should be greater than equal
Okay.
greater than 0. It shouldn't be greater than equal to 0. It should be greater than 0, right? Is that correct?
Yes, sir.
So this is one of the assumption, and this assumption is called linear separability with gamma margin, right? These are okay. There are two more assumptions we'll uh, do, and then what we can do is we will see
Club
that,
them together.
yeah, some of all these assumptions, and all with those assumption we'll try to figure out new algorithm, new perceptron algorithm, or new some other kind of algorithm. Basically that is going to be your support vector machine algorithm, right? But yeah, so here what should we do now? What is the second assumption? There is another assumption which is called as a
Radius.
radius assumption. What does it say to me?
So,
Yeah,
Outermost point should be maximum or separate different away from the center.
yeah.
All points
Outer.
are upper limited by the distance of the outermost point.
Yeah. So what is it? It is saying is, let us say this point is there, right? So if whatever the so this is the farthest point, right? In this data set. If you look at,
Basically, length of the farthest point from the center date.
yeah, or you can say that all the data points which are there, like even the positive or negative, they should be within that circle, right? That is
Yeah.
what your radius assumption is saying. And let us say whatever this is going to be the farthest data point, which is like in this data set, we'll have to take that data point, and all the data we are assuming that are within this uh, circle, right? So what is that assumption here? For I, or for all I belongs to the data set, they should satisfy the condition that summation of or okay, norm of xi, what
Should
does
be
that
less
mean?
than
Xi is
L2
the
norm.
distance
point.
L2 norm should be,
less than or equal to r.
and what is that r? R is like this r.
Radius of the outermost point.
Yeah.
excuse me, sir.
Yes.
I didn't understand W transpose Xi into Yi. It should be greater than or equal to gamma.
Okay, fine.
Is
So
it an assumption or is
yeah,
it something that?
this assumption. Okay, initially in Perceptron, what we were saying that W transpose xi, or we are saying that sign of W transpose xi should be equal to yi, right? Is that correct?
Yes, yes,
Okay.
yes.
In that time we are saying that, okay, what does that mean is, uh, if you have this line, right? Okay, maybe I'll just take some other page. So let us say we were saying that if this is the W, which is actually separating my data set, and what is the line here? This line was there, right?
Yes, W transpose
This is W
X.
transpose X, right? We are saying that whatever, uh, what is this part? Let's say this is the positive class. So this is, can I say that it is okay? This line is, what is the equation of this line? W transpose
W
X equal to
transpose
0.
X.
Whatever the data points this side are there, they will satisfy this condition, right? W transpose Xi greater than 0.
Yes.
Why I'm saying this is because let's say whatever the data points are here, this line is W transpose X equal to 0. If I draw any line here, what is the equation of this line? W transpose X greater than 0. Okay,
Greater than 0.
or some other lines, right? And all these data points will be on these lines, right? All these lines. So can I say that
Yes.
all the data points which are uh, like okay, or whatever the data points, let's say any data point, they will be on the lines which satisfy these conditions, right? W transpose X is greater than 0. Is that fine?
Yes.
Right. Similarly, all the data points here, all the data points here, right? They will satisfy which condition? W transpose X
W transpose X less than 0.
less than 0, right? Is that fine? Okay.
Yes. Yes.
Okay, and then we said that all the data points which are on this line, they are also, we will say that they are positive, because we are saying that if any data point which is W transpose X is greater than or equal to 0, that will be treated as positive, and
Positive.
W transpose X is less than 0 is negative. But that was getting the problem of this kind, right? This kind,
Yes.
right? So where we were not able to converge. So what we are saying that the data point shouldn't be on this line, they should be at least some margin away from the line, right? Okay, and we said that some gamma margin. So the data points should strictly be where they can be on this line or this line. They cannot come into this region. Is that fine?
Yes. Yes.
That's okay.
Yes, sir.
Or and the similar margin will be applicable this side also, and we are saying that okay, this also is gamma, and all the data points which are here, they can be treated as negative. They shouldn't come into that zone, right? Okay, we are saying that that shouldn't be a zone. This data point shouldn't be there. So what will be, okay, what is the equation of this line then now? It's W
W
transpose
transpose
X equal to gamma,
gamma. Yes, sir.
and this one is W transpose X equal to minus
Minus
gamma.
Minus
gamma.
gamma.
So whatever the data points which are actually this side are there, what is the equation for them? W transpose X greater than
1.
or equal to
Gamma.
right?
Okay.
Is that fine?
Yes.
If
Yes, sir.
this dotted line is W transpose equal to gamma, so whatever the data points, they are always be greater than or equal to gamma, right? All the data points or all the lines which are there on that side, fine. All the lines this side, they will satisfy this condition, right?
And sir,
Yes.
the total distance between the two hyperplanes is supporting hyperplanes is called as
That is the
what
width,
terms?
width, width,
Width, right?
width. That we try to maximize, right? In SVM.
Hmm.
Right. Okay, but that okay. We'll come to that like after few minutes. But what is the equation for this, or which or these all the data points which are on this side of the gamma or this line? Which equation they should satisfy? W transpose X is less than
Less
or
than
equal to gamma.
Less
gamma.
than or equal to minus gamma.
Minus gamma or
Minus gamma, sir.
yeah, minus gamma.
Minus gamma,
Okay,
yes.
that is fine, right? Then I think that minus gamma, if it is there, then it should be like this, right? Greater than or equal to minus gamma, right? If you think about
Yes.
the number line, so 0, -1, -2. So is -2 greater than -1? It's not like
No, it
Yes.
should be then or
Sir, is
equal.
yes than. So
Less than,
it is
less
both
than,
yes
less
and
than.
minus 1. So
huh?
Less than or equal to
-2 is
Then
minus.
it
yes
will
and
be
minus
less than or equal to.
Less than or equal to minus gamma, or less than or
So
equal to
it will be
gamma?
W transpose X Y will be greater than
Yeah,
equal.
yeah, that is true. Yeah, that is correct. Okay, okay, fine. So let us say it is what you're saying is it should be
Less than or equal to minus gamma.
less than or
Minus
equal to
gamma.
minus gamma, right? Okay. So what we are trying to do now, that whatever W transpose, we'll try to find out like its commonality. So for this, it will always be positive, right? So this should be the positive quantity. So if I just multiply with its label, what will happen then?
It'll always be positive.
So this actually here it is all positive, so it is greater than gamma. And if I just multiply with this labels here, so it will always be the negative labels, right? So this quantity will become what? This quantity will become
Okay.
negative, right? And then I'll just say that it is greater than equal to gamma, right? Now this is fine.
Okay,
So
sir.
so we are saying that W transpose Xi into Yi, right? If I just multiply with its label, then it should be greater than equal to some gamma. Is that fine? This condition is going to satisfy now.
Yes, sir. That means whenever we are finding the W transpose Xi, when we multiply with its corresponding label, it won't change the condition of
Or
greater than or equal
yeah,
to
yeah,
gamma.
because
Or,
then we will be on this side, right? Okay, correct.
yes, to ensure that we are multiplying it with its corresponding label. Is
Yeah, you
that
can
right?
say like that, or yeah, in the that way it gives us the like similar kind of constraints to both sides, right? It's like mathematically it will be fine, right? uh, or yeah, we will be able to analyze it better that way, right? Because we cannot write two separate conditions, right? Anyway, that is going to be the same thing. Fine.
Okay, okay. Got it, sir. Thank
Right.
you.
Okay. Now that was the second condition. That was the first. Okay. This was the linear separability condition with gamma margin. What was the second condition? We are saying that all the data point should be within that radius. That radius should be like the farthest most data point, and all the data points other than that will be in that circle or ball. Right. Okay. And the third one will be what?
Norm of W will be equal to 1.
Yeah. So what we are saying that whatever the optimal solution is there, the length of that optimal solution should be equal to 1, right? So we are actually trying to uh, constrain that part, right? So what we are saying is whatever W are getting, so this, let us say this is the W star, the norm of W1 should be like, we are saying that it should uh, be able to within
What is
this
W
part.
star over here? The one we said is
Optimal
optimal.
solution. We are saying that this is the optimal solution.
The star here refers to optimal. W
Optimal.
optimal, norm is
Yeah.
equal to 1.
Yeah. Right? Okay. Is that okay?
Yes, sir.
Okay. So in
So
that,
all these three assumptions are the conditions that we are making for when the perceptron is not converging, right? So
yeah. So the first condition we made is to because it was not able to converge for all, right? All scenarios. Then we made this gamma margin condition, and now we are just making two more conditions, because that way it will be easier for us to maybe develop the new algorithm. Is that fine?
oh, okay, sir. Okay.
Yeah. So because see, our goal is always to be what? To get uh, correctly classification, like correct classification. Even with, so now even with these conditions also, or these assumptions also, what is the problem? If you think about it, we are able, again we are in the same zone of that what, linear separability. If any outlier is uh, will be there, let us say some negative point is there, will it be able to classify it? Still no,
No, sir.
right?
It is not
So
robust to outliers.
yeah, so then that's why we come to that part like soft margin SVM, which will be able to accommodate that. So we are slowly building towards that. This is like anyway, we are not using these algorithms anywhere, right? Mostly in practical situations, what algorithms we can use is soft margin SVM. That's fine. But
Okay,
this
sir.
is the process where, okay, we are actually since we had some problems, we are showing that okay, this was the classically these problems happened, and how we are trying to uh, remove those issues and get a better algorithm, right? Okay.
Okay.
So this here, if we fit all the
Okay,
outliers, will it?
your voice is very low. I don't know why. Is there problem in your mic?
Hello,
Yeah.
I'm audible.
Yes. Yeah.
Yeah, I was just asking that if we fit all the points, like even the outliers, then will it not lead to an overfitting problem?
Overfitting problem you're talking about, right? Okay. Uh, it will be, but let us say, but in general, right? You if you have like one or two outliers, see, it's not about fitting the algorithm, right? Or fitting the algorithm in this case, at least not in this case. Why I'm trying to say is, this is not the linear regression type of problem where we are actually trying to fit everything. This is a classification, right? So generally what you wanted to do is you wanted to classify as much as possible, right? As much correctly as possible. But let us say if you have only one outlier in your case, and if you are not able to, because of that, if you are not able to use that algorithm anyway, if any in this case, any outlier will also, if any one outlier will also be there, will not be able to use this, right? Let alone that perceptron, sorry, let alone that overfitting problem. With one outlier, if it is there, then this algorithm will not work. Why it will not work? Because the assumption was that the linearly separable condition, if the data is itself is not linearly separable, we will not be able to apply this algorithm like at all, right?
Okay.
So
Fine.
that is true, your understanding is true if you wanted to make it like, but here we are using the linear condition only, right? We are finding out the w only, we are not going to find out any w square or something like that. There we are not actually going. So overfitting problems occur when you're trying to use some other more like, so linear is the basic fit, right? Basic polynomial. If you go for like higher order polynomials, then you will try to overfit now, right? And then you will try to get the curvature of the curvature for the this w's, right? Then it might be a problem. Fine. So what will, okay, I'm not going now into the details right now. So what we can do is we'll just try to find out, uh, can I skip some of the parts, or do you want me to explain everything here? Not-
Which part, sir?
So there is like, okay, so there is like a lot of derivation is there to find out. So I'm not, maybe I'll not go there. I'll just try to tell you what are the number of mistakes. So the Cauchy Schwarz inequality and all these things are there, right? I will not go into the derivation. Maybe you can check it later. It's already there. So the number of mistakes this algorithm does is now what? It is bounded by what?
R square by gamma square.
Yeah. So
Gamma square by R square.
r square by gamma square, not gamma square by l square,
Okay.
r square by gamma square, right? So I think there is some mistake in the lecture where sir has said like L is the
Gamma
number of
square by
mistakes,
R
right?
square.
But number of mistakes are equal to L plus 1, not the L, right? That was the problem. But okay, anyway, that is
And
not a big
why
issue.
L plus one we are taking here?
Well, that's what I wanted to tell you. So if you, uh,
Because
I
in
need to,
lecture, sir has told
yeah,
L less than equal to.
yeah. But there was a problem. Why? Because I'll tell you. Okay, I'll just tell you one thing. So you know, right, from the
Sir,
second,
what is L plus 1, sir? What is L here? I
you
didn't get.
guys have you guys gone through these lectures?
Not very well,
I
sir.
mean,
Not
T
very well.
is less than or equal
Okay,
to
okay,
R square by
okay. I'll
gamma
tell you.
square, where
Okay,
T is the
okay.
number of
Maybe I'll
mistakes.
just,
I don't know.
L is the number of mistakes.
number of mistakes or number of updates happened, right? So let us say WL plus 1 is equal to, what is the update rule? WL plus XY,
X
right?
I X Y.
Yes, sir.
XY.
Okay, so norm of WL plus 1 uh, is equal to norm of WL. So this is like L plus 1 is the L plus 1th mistake, right? So if I wanted to find out, so it will be like XY. I'm just, okay, I'll try to go it like little bit faster. In linear algebra terms, what it will be? This part will be
Cauchy Schwarz less than equal to
WL plus XY transpose
Transpose into WL
to
plus X.
WL plus XY,
That's XY.
right? Okay, and now uh, you will have to okay, just then if you just expand this bracket out, what it will happen now? It will be WL transpose into WL, right?
That
Right,
is
first term
1.
will be,
Yeah.
so that is WL norm square
Norm square.
plus 2 times
WL
WL
into
As
transpose
transpose.
X
X
into
into
Y
Y.
plus norm of
Yeah.
square
Norm of
y square, right? Because it will be X transpose Y into XY, right? X transpose Y into XY. Basically, it will be X trans or sorry X. This is like XY transpose.
XY transpose.
So that will basically it is Y transpose X transpose XY. This X transpose X is basically norm of X square, right? And Y anyway
Y is a
constant.
scalar.
So scalar multiplication you can do anywhere, right? This is the term, right? But we say that why we go to L plus 1th update, because this was incorrectly classified, right?
So this is negative.
And this will always be negative. This will be always be negative quantity. Why?
Because
Then
the
if
sign
it
of
is
W transpose X and Y are different.
are different, right? If they are different, so even if this is positive and then there was a mistake, then that means it was mistake was negative, right, for Y. So the product will be negative. Let us say if it is if this product is negative, then it was, since it was incorrectly classified, that means the correct label was positive. So anyway, the product of this term will always be negative. So, and is this a positive quantity?
Yes, sir.
Yes, because it is
Yes.
square. Is this a positive quantity? Yes, because it is a square
Yes.
again. Right. So if these squares are positive, and like if you are subtracting some negative quantity, that means it should be less than or equal to. So the bound will be there, and the bound will be WL plus 1 norm square should be less than or equal to WL square plus norm of X square plus Y. Sorry, not. Is that
Y
correct?
square is also 1, sir. Y square is also 1.
Y square also 1. Okay, yeah, that is correct. Because
X square
y
less than
can
equal
be,
to R.
yeah, y can take only plus 1 minus 1, right? So square of that
Ah,
will be always positive.
positive, yes.
And what is and according to our
R square.
radius assumption, this will
Square
be
R square.
WL square plus R square. So it will be WL plus 1 norm of square. So that should be like WL square plus R square, right? Now, if I, okay, then this is one condition, right? Okay, this keep it here as it is. What will be WL square? That should be equal to WL minus 1 plus
Great.
X, XY, right?
Yes, sir.
Correct?
Yes,
Mm.
sir.
Because that L minus 1, that thing. So if I just do it again, what will I get now? I'll get
WL
WL
minus 1
minus
square
minus
plus R
1
square.
square
square
plus
plus R square.
R
R
square.
square. Less than.
So
Less than or
this is
equal to.
equation 2. Then that means WL square I can actually replace with this part, right? Right? In the equation 1. So that will be
Mm.
what? So WL plus 1 square will be WL minus 1 norm square
Square.
plus
Plus 2
R
R
square
square.
plus R square is 2R square, right?
Mm.
And that way, if I go till
Less
WL
than or
plus,
equal to, right, sir?
yeah,
Less
less
than
than,
or equal.
so WL plus 1 norm square should be less than or equal to, I'll go till what?
0.
W0, the initialization term, plus then, okay, this here is a mistake. So it will be how much R square? Will it be LR square or okay? Can somebody who's having that issue with the mic, can you just help?
Yeah, LR square.
Yeah, sorry, because it's irritating, right? For me to, I'll need to speak like more loudly. Okay. So here it is W0 or W naught square plus LR square or L minus L plus 1 R square. I'll tell you now. Let us say W5 equal to what? W4 plus R square,
R
right?
square.
W5 equal to W3 plus 2R square.
Mm.
Then it will be W2 plus 3R
3
square.
R square.
Then W1 plus 4r square,
Yes.
and w0 plus 5r square, right? And that is equal to w5. So if it is wl plus 1, then it will be w0 plus
L plus 1.
L plus 1, right? Because whatever the update here is there, it should be L plus 1 R square. So here it is L
Okay.
plus 1 R square. So in the lectures, I think it is L R square written,
Yeah, yeah.
right? So it shouldn't be like that. It should be L plus R square, right?
Hmm.
And I think there was some another condition on the margin was there. There also the mistake, same kind of mistake happened, where the second condition is what is the multiplication, right? So W1 transpose W star, right? That was the case, right? So it should be equal to what? WL plus 1, sorry, WL plus XY transpose W star, right? And in that case also, it should be actually greater than or equal to WL. Uh, okay, so can I what can I say about this? Okay, let me do it like quickly. If I expand these terms, what will happen? WL transpose W star, right? Plus W star
X transpose.
transpose X
Same thing.
Y, right? Same, because it's a dot product, right? It's commutative anyway. But we have that condition of W square, right? So this length of this W will be equal to or norm of W equal to what? 1, right? Oh, sorry, it should be
W star.
okay,
W star.
that should be W star. Okay, so that is not there. Okay, that's okay, not an issue. What about this part? This negative or positive, or what is it? It should be greater
It
than
will
or
be
equal to
always positive. It will be always positive.
uh, because it should be greater than or equal to
Gamma. Yes.
gamma. That is our linear separability with gamma margin condition, right? We have that gamma margin condition. So can I say that it is this term is now not equal to, it should be, we can do it right like that. It when it will be equal to, then when it is WL transpose W star plus gamma, right? Why it is greater than equal to gamma? Because we have said that uh, this is the condition, right? So each of this should satisfy this part, right? WL or W transpose Xi Yi should be greater than equal to gamma, and every update that should satisfy it, right? That W has to satisfy that, right? So if I wanted that greater than equal to gamma, then in that case it should be uh, greater than or equal to gamma. I hope this is fine. This case is okay, right? So in this case also, what will be the next part? What is the WL transpose W star? Let us say this is equation 1. Okay, so okay, so it is WL transpose W star will be greater than or equal to WL minus 1, right? WL minus 1 transpose W star plus gamma. Is that correct? So from equation from 1 and 2, can I say that WL plus 1 transpose W star should be greater than or equal to WL minus 1 L minus 1 transpose W star
Gamma.
plus
Gamma.
2 gamma, right? So again, similarly, if I uh, go till 0,
W0.
W0 transpose W
W
star
star.
plus, now here it should be
L
L plus,
times gamma.
no, it is L plus 1 gamma. A
Okay.
similar argument I can tell you, right? The whatever argument we have seen here, can we do the same argument here also? Yes. That is what the mistake is there in the lectures, right? Is that correct?
Yes.
So now I can say that WL plus 1 transpose W star is greater than equal to, but W0 is a 0 vector, right?
Yes.
Yes, sir.
So this quantity will become
Zero.
0. So can I say that now WL plus 1 transpose W star should be greater than equal to L
plus 1 gamma.
is it fine? Right?
Yes, sir. Yes, sir.
From Cauchy-Schwarz inequality, what we have known? What is the Cauchy-Schwarz inequality? So any dot product with the of the two vectors, and if I take a square of it, it should be less than or equal to
Norm
norm of
of x
separate, yeah,
and norm of y.
right, y square. So this is my Cauchy. Okay, I don't know what is spelling. Okay, Couchy Schwarz. I think something like that, right? So okay, it is Cauchy
Sir,
Schwarz
its
inequality.
modified version is like whole mod x plus y whole square.
What is it?
X plus y whole square
Where?
is less than. I mean, Cauchy Schwarz.
No, it is X transpose Y, right? Basically, it is. I think we have learned in MLF also. It is A transpose B. So that is a dot product between A and B vector should be less than or equal to norm of A square into norm of B square, or it can be equal to minus of,
Minus.
right?
Yes.
You if you remember it, but we don't need this side of it. We just need one side of it, and that can be proved from Pythagoras theorem. But okay, that is not a problem. That is not the important thing for us. Uh,
So,
hmm,
sir,
hmm.
so that means the norm of WT plus 1 square will always be less than or equal to WT norm square plus R square. But when there is a initial W0 weight vector, then we can find it using T plus 1. I mean, we can add that W0 norm square plus T plus 1 into R square. Am I right, sir?
Okay, I think you all you said a lot of things. I was not able to
Uh,
follow up that. Yeah.
Okay, sir. So what I meant was there is this initial formula that WT plus 1 norm square will always be less than or equal to WT norm square plus R square. But when we are given W0, W naught square, the
Hmm.
norm, then we can find the WT plus 1 using W naught norm square plus T plus 1 into R square. So both the formulas are valid, no, sir, was my question.
Yeah, that should be there. Yeah, but actually we don't need that part also, right? That is correct, but we don't need. Why we are doing this is to understand what are the like bound on number of statistics, right? So okay, so here I think I didn't mention it. What is this WL plus one? The final thing. Okay, maybe it
W
should
plus
be
one
like,
is the pre-final thing, right, sir? W
yeah, yeah,
star is the final thing.
yes,
And
yes, yeah,
is that correct, sir? Okay.
correct, correct, correct.
Can we please go ahead? Then?
So now, from this equation, what can I say about it? From these two equations, can I be able to infer something? Like if I take a square of this, can I think
Square.
of this as one x and this as y?
Yes,
So
sir.
Yes.
So we have a lower bound, upper bound, sorry,
yeah.
for
So
that.
if I take a WL plus one transpose, right? Or okay, in this way, let us say it is
Norm of
W
WL plus
plus
1
one
square.
transpose into W star. If I take a square of it, what should it be?
WL plus 1
It is W mod, okay, norm of
is
WL
WL
plus
WL
plus 1
square
square
plus,
W star
not
square.
plus, sorry, not
zero.
plus, uh,
That will be one W star.
Yes, so we
square,
can cancel that out.
right? That is one anyway, but okay, for now this is the case, right? If I use the Cauchy-Schwarz inequality from this equation 3, what can I say about this quantity?
It is less than or it is
No,
greater
not
than
uh
L plus 1 square R gamma square. It is greater than L plus 1 square gamma square.
so, or can I just directly substitute this part, or like if I'm able to do it? Okay, fine. So can I say that? Okay, let us say what can I say? Can I say that it is L plus one
Square gamma
gamma
square.
square? Is that fine?
Yes, sir.
Any issues here?
No, sir.
No.
Right, because these are the same things. So and this is equal to one.
1.
So if I just anyway, this quantity is always be less than or equal to. So same thing is there, right? So can I say that WL plus one norm square is always be greater than or equal to L plus 1 square R square.
Gamma,
Sorry, not R square, gamma square.
gamma square.
Is that okay?
Yes.
Yes.
Right? Okay, this is fine. I hope no issues till this part.
Yes, sir. Yes.
Okay, this is the case now. Now what else I can do? So I'm just putting it as, let's say, equation 4. From here, what I can say now, WL plus 1.
Plus one square is less than or equal to.
So norm, right? So norm square. So length of this square should be less than or equal to
L plus
L
1
plus one R
square
square.
R
L
square.
plus one into R square.
L
L
plus
plus
1
one into R square.
L plus
or
1 square.
square,
Round.
right? Because whole square we are doing, right?
It is L plus one, I think, sir.
Mm, okay, I think, yeah. I think we just, okay, yeah, it is L plus 1 separate and R square, not square. It's already in that terms, right? Is that fine? Okay. This is another equation we have found out. So let's say equation 5. What can we say about now, about from equation 1 and sorry, 4 and 5?
L
So
plus one square gamma square is less than or equal to L plus one into R square.
so can I just write down here? Will that be like this?
Yes, sir. L plus one square gamma square.
Is that fine?
Yes, sir.
Because WL plus 1, this length is always be greater than or equal to this part. So this is the same thing from 5 or from 4, and is already been there. So what can like again we can say safely about this is like L plus 1 square gamma square is less than or equal to L
L
plus 1
plus one
R
into
square.
R square.
Is that okay?
Yes, sir. That means L plus one is less than or equal to R square by gamma square.
So that means uh, this one and this one will get cancelled. So I can say that L plus 1 is less than or equal to
R
R
square
square
by
by gamma square. But what is this L plus 1? Is
Number
the
of rounds.
number of
number of
rounds,
Plus
but
mistakes plus one. Plus one.
no, not plus 1. This is the number of mistakes. That is
Okay.
what where the wrongness is there, right? In the lectures.
So instead of WL plus 1, we could have also done
With the
WL.
WL, and if you go
Yeah,
with the WL, then it
yeah,
will be L is less than or
L
equal
is
to R
equal to,
square
yeah.
gamma square.
Yeah.
But it is so
Yes,
Taking in
when
the
account.
notation
yeah.
was confusing for
Yeah.
me.
So WL plus 1 was, we have seen like WL plus 1 is W L plus 1. So what is it? WL into XY, right? We have gone through this update rule. If you use this update rule, then you will get L plus 1 as less than or equal to R square by gamma square. But if you use WL equal to WL minus 1
Minus 1, yeah, you get L
plus
is.
XY, then you will get this. And that is also number of mistakes. It doesn't matter, right? Anyway, it's like how you are choosing the this part, the number of, anyway, this L plus 1 is basically the number of mistakes or number of updates we are doing, right? No.
So
Yes,
this
sir.
L plus one is the number of mistakes that we make.
Yes.
Yeah, L plus 1 is a number of mistakes. Actually, we could have started with L and gone L minus 1 onward, so we would have got L less than or equal.
I think that's fine. It's just convention, right? In the end.
Yeah, that is
L plus
that
one is
actually,
the number of mistakes we've made, right, sir?
yeah, but
And
finally what is the thing, like whatever number of mistakes you do, that should be bounded by R square by gamma square, right?
right.
That is the thing, right? That is the important thing we'll have to do. And when you say that it is bounded by R square by gamma square, what does that again mean? Is that you are able to
Converge
converge,
always.
right? It will always converge. Fine, right?
Yes, sir.
Any issues? See, I'm like, I think we are getting like a lot of so okay, that's fine. I didn't think that you are, but this is okay. Maybe you have seen for the first time, it will take some time, but that's okay. So maybe what I'll do is I will not be able to cover all the things. I think we have so many things left, but we'll try. Okay, I'll try to finish it off whatever I can do. This is fine. So can I directly say that in case of perceptron with gamma margin, so I'll summarize it once more for you. What is the summary? If I go with the linear separability condition, so there are three assumptions for perceptron algorithms. What are the three? One is
Linear separability.
linear
With gamma margin.
separability with gamma margin. Second,
Radius assumption.
radius assumption. What is that?
And xi square is less than or
Is
equal
greater
to
than R square.
r.
Not equal, greater than 0. Third is this
W norm of W star
W optimal is
equal to 1.
equal to 1.
right, or you can square also. That's not a problem. With this case, with these assumptions, we can say that the number of mistakes that can happen are equal to or are bounded
They are
by
less than or equal to r square by gamma square.
square, and this is a finite number, right? And if this is a finite number, that means now we can say that perceptron
Converges.
is it okay? This is the crux of
So
whatever we are discussing.
here the iterations or the number of mistakes are they same or
Yeah, you
is it
can think
different?
of iterations also, or the see number of mistakes and iterations. What is the, so how you are taking it, it depends on that, right? If you are thinking that one pass through all the data points is one update, or if you are thinking that whenever I'll get a mistake, that is one mistake. One pass through data points, you understand. Let's say we have taken that example, right? The 4 data points were there. So if I go through x1, x2, x3, and x4, if you are thinking that as one update, or if you are thinking as like whenever I do a mistake, that is one update. Basically, whenever I do a mistake, that is one update, right? And can I say, so iteration will be what? Iteration generally means if you pass through all the data points, right? So,
Yes.
yeah, don't get confused with that. These are anyway the so iterations mean generally
So whenever we are changing the W,
that is
then it
update.
is
Consider as
yeah,
update.
update or mistake.
Update or mistake, and that is bounded by this, and that means anyway somewhere we are going to get the convergence. We and this is now for all the cases, right? Is that fine?
Because in one of the assignment, I think they have given that the number of iterations are greater than or equal to number of mistakes. So here, I think it is we have to consider it as whenever W is changing, it
That is
as a mistake.
mistake, and that is bounded by r square by gamma square, right?
Yes.
Because
Okay, so
because the
got it.
update rule is applies only when we do mistake. Otherwise, we don't update, right?
Yes, and W L plus 1 refers to the W whenever there is an update going on, L plus 1 iteration. Is that correct?
Not L plus one basically. It is okay. L plus one update. Okay, I'll tell you
L
what.
plus
No,
1.
Don't worry about
just to
that.
confirm, the final optimal solution will be the L plus 2 solution, right?
No.
The L plus,
L plus one. No.
huh?
Okay, I'll tell you. Okay, I'll tell you. X1, X2. I think all of you are joined now only, right? You didn't join the previous sessions, I guess.
No,
I
sorry.
have watched all your sessions, sir, but there when I was going through this formula things which was
So
given
in
by
the first
Okay.
iteration, you are calculating W1, right?
So
The
let us.
first iteration, you are
Okay, don't
calculating
worry. Okay.
W1.
So leave about all these things now. Don't. I will tell you now. Then after that, you can ask me the questions. Okay. So this is the initialization, right?
yes.
Okay. If let's say for the what you do first, then is W transpose x1 equal to 0, and you see that whether there is a mistake or not. Let's say there is no mistake, right? Then you check for W star x2 equal to 0. There is no mistake. Is that correct? Not correct. I'm
Yes.
saying that it is not. Let's say there is no mistake. Now, when I go through W star x3 and it was equal to 0, I found out it is a mistake. Why mistake? Let us say whatever the sign of this is, that is not going to be equal to y3, right? This mistake
Oh,
happens, and then I do w1. W1 will be w0 plus
X3Y.
x3y3,
X3Y3.
and that will be your W1. So this is the first update, right?
So in first update we get W1, like that in Lth update we get WL.
Yeah, so L plus
Oh,
one update will be your WL
L
plus
plus
whatever,
x3
not
whatever.
x3
Yeah.
y3. So it should be, I should, it can be x1 y1 or x2 y2, we don't know, right? The
So
thing
in
It
is,
will be L plus
L
one.
plus 1th update we get WL plus 1.
Yeah.
so this is the mistake, right?
Yes. So in WL
So when
plus
I
in
say WL plus
L
1,
plus 1th update we get WL plus 1.
yeah,
Yes, sir.
so
Both are same. The
yeah, so
update and
why you are confusing that much, I don't understand. It's like, it's very clear, right? WL plus 1 is the final solution,
Yes.
yes. Because
right?
the L plus one was giving confusion. Initially we took it as WT or like
Right,
WL.
right.
So
Okay. So L plus 1 is the final solution, and N plus 1 is the number of updates also. So
got
let us
it.
say in this
Sorry,
case,
sir.
let us say in this W1 is your final solution. Let us say, assume that it's the final solution. So, uh, right. So if this is,
Number of mistakes you make is
so
1.
number of mistakes is 1, right? Like
One.
that you can understand, right? So when I say WL plus 1 is the final solution, then in that case, how many mistakes are there? L plus 1.
L plus
1.
one.
If I say that WL is the final solution, then how many mistakes are there? L.
L.
It is like, because this case is, and this thing is always WL. Either
Minus
you
1.
can think L minus 1 if you think this as L. If you think this as L plus 1, then this will become L plus 1 minus 1, which is basically L, right?
Yes,
Yes,
yes.
sir.
So that's how. So it's just not like you don't have to worry about that. I know why that confusion happened, because in the class it is clearly mentioned that number of mistakes equal to L, and when that update is actually WL plus 1, right? But
Yes, sir.
that is
The
wrong.
notations are different
Yeah,
actually.
that is
So
wrong. That is wrong. Yeah, definitely that is wrong. I hope that is now clear.
Yes, sir.
yes, sir. Thank you.
Okay. So this is it for uh, your perceptron thing. We'll have to go to the. I think you will have to see for the next thing is what, I think the margins. But I think before that we had one more point, which was logistic regression. So what I can do is today I'll finish with logistic regression. We stop there, because I think then it will go like beyond some point of time. Tomorrow again we can have the session, maybe 1.5 hour. We can continue
So
there.
day after tomorrow is there.
Yeah, but that
Tomorrow
will
also
be
will be
11.
Tomorrow,
tomorrow also will be.
tomorrow there is already like session.
Then I don't know, if I try to complete this, then it will take a lot of time, right? I don't know what you do. You should tell.
You can take a morning session, sir, because evening
It's
we
a
have
morning work.
pre-working.
Morning.
Morning will be
Yes,
better.
sir. 11, 12.
So
Or
anytime after
9 to 11
6.
Tomorrow,
or anything.
11 to 12 p.m.
morning.
Yeah, I
Then
think
a
it will be
session.
tough. Okay, just I'll just see, just a minute. I'll check and come back. Okay, so okay, just a minute. Huh? So what should I do is maybe we can do a session tomorrow, right?
What time, sir?
Yes.
Morning, okay. If you want morning, we'll do it from 11:30, right? I'll add it.
Okay.
That also, that also works, sir. Please add a calendar event just in case.
Ah, right, right.
Not a long session, sir. Even 1.5 hour is enough.
Yeah, 1.5 hour. We'll try to finish it off. So I know now also I'll finish it some parts, and then we'll do. Uh,
So,
right? Okay.
Yes.
So,
Or sir, you can increase the length of that next session.
no.
And
Then it will be like I'll also have some other things to do, right? You,
oh,
okay, so it will because I need to do some meetings and all. So that night I might not be able to. Fine. Okay, that's okay. So shall I complete the logistic regression first, or shall I go to, or we can do the logistic regression later? You just
what
tell
would
me.
be better,
Tomorrow
sir?
only you can take
Just
some.
brief
It's a
out,
fresh
sir.
mindset.
So
No, now I'm asking, not tomorrow.
later, sir.
you can brief it
Later,
off
sir.
and complete it, sir. Week 9.
Because if we will do it shortly, then we won't be able to understand. I mean, revision won't be
We,
able
so,
to
so just to
take
confirm,
place.
week 9, how many topics do we have here? We have logistic
No, we
regression.
have only logistic regression now
Yes,
remaining.
sir. So,
Right.
I think most of us can
See,
stay till 10:30, right?
yeah, that is what I'm trying to say. So
Yes.
otherwise, see why I wanted to take the other one is because that
Yes,
is
sir.
very related to our whatever we have discussed it, right? So that will.
Yeah, the SVM, sir, right?
Hmm.
If that is the case, yes, we can in say 20 minutes we have right now.
Yeah. Okay.
Everyone,
No, I'll take
we can
one
cover
topic.
SVM and short. Yes,
Yeah.
sir.
No.
One short topic we can do.
Yeah, and then we'll do tomorrow, right?
Yes, sir.
Okay. So number of mistakes we have said. Then so that's why we can get more time tomorrow morning, and then we'll do some more things, right? So if you have any other doubts also, we can take. Fine. Okay. So number of mistakes by perceptron algorithms will be how many?
Less
L
They are
plus
than or
one.
bounded
equal
by
to.
they are bounded by r square by gamma square.
Yes.
That is what we have
Gamma.
said, right? And now we have already said like okay, these are the assumptions, and what was the assumptions?
Linear separability of gamma margin.
Should be this is radius assumption, then linear separability with gamma margin,
And
and
norm of W equal to 1.
norm of
Norm of
w
W star equal to
Optimum.
1.
to 1, right? And then what does it get to us? That will lead to a solution where w transpose star xi also okay with these assumptions and with this convergence. What we can say that we
W
can say that whatever the optimal solution we are getting, that will able to
correctly
correctly
classified
classify all the data points and with
greater than or equal to gamma.
right, and this for all I, and gamma will always be greater than equal to 0, right?
Greater than 0.
Greater than 0, right? So this is the condition. Now we need to check whether okay, what are the again the issues with this is what again this the issues of those like if I started with some data pair, we will get different w's, right? Will that be solved by using this?
No.
No, right? The still that will be there, right?
It's an
I
order
will,
sensitivity essentially, right, sir?
right. So again the whenever we start with something, so some different pair of x and y, we are actually ending up getting some other
W
w.
star.
So that is still there, right? The only thing we are able to prove is that the convergence, right? So that means with these assumptions I'm able to get some solution, right? I'm getting some w, but will that be a
Optimal
good,
W.
yeah, optimal w or good w? That is the problem we'll need to solve still, and that is what actually called as the quality of the solution. So we are getting different solutions, but whether all will be the final fine solutions or there will be a specific solution which is a good solution or optimal solution. What does that mean by? We'll try to again see that. So okay, where we are currently converged now, or at least we said that we are fine with, is that the data points are such that they are linearly separable, right? Correct?
Yes,
Yes,
sir.
sir.
These are some data points here also, and all these data points are, and what we are able to get some margin. We are saying that W should have some margin, right? Suppose this is some W star with, let's say, within one, right? So that this answer is always be there. So what is the W here? Okay, or sorry, what is the line? Sorry, I said this line is there, right? What is the equation of this line? Let's say W star. Okay, maybe I'll say that W1, W1, W1 transpose X, right? Equal to 0. Is that correct? And we are saying that there are lines which is uh, with some margin, right? Okay, so that let's say that margin is this. Okay, I'm just saying that this margin is okay. Don't worry about the distances. These distances are equal, right? Gamma and gamma. Is that fine? We are able to separate this data by some margin, right? Is that correct? Uh, this is also is this a good or is this a possible solution?
Yes,
Yes,
sir.
right.
Yes,
This is
sir.
a possible solution. Okay, I just draw one more solution. Say this is W. Okay. So what is the line? Which is the line here?
YX.
Y-axis, y-axis.
Or I can say that x2 axis. Okay. So this is the line, and if I wanted to plot some margin, I'll be able to, let us say this margin. This is the margin, right? Some, let's say, gamma 2 or gamma 2, and this was, let's say, gamma 1. No, let's duplicate. Fine. So this is also the possible solution, right? These
Yes.
two are also the possible solution. But now, again, I don't want that kind of thing, right? Let's say I have started with some data points, you have started with some data points, and we both are actually ending up into different solutions, which both are feasible. But what I wanted is, I wanted, like, whenever we start with any data points with anything, we should be able to, so both me and you should be able to uh,
Common solution.
get a common solution, and or what, and that common solution also should be a optimal one, right? So like that is the best solution we wanted to find it out. Is that correct?
Yes, sir.
And what that best solution should be? So the
Is
margin,
the largest
what,
gamma.
yeah, we
Largest.
should have largest
Largest. Yeah.
margin, right? So why that largest margin is there? What is the use
Because
of
that
that
is
largest margin?
It
that will be
generalizes
able to
better.
properly generalize.
Less mistakes.
It will be
uh,
able to generalize the points better.
Mistakes is not a problem for me, because mistakes is okay. But let us say uh, this is the region, right? So blue color is the region with W1, right? Yeah. I don't know where it is, W1. Okay, this is the W1 region. Okay, fine. And suppose, okay, I don't know whether this, okay, I'll just draw it properly once. Okay, you had, let's say, this W1, and with this W1, suppose I have this margin. Is that fine? Is the margin? Is that okay with the W1? And you have, let's say, another solution which is let's say W2, and I have some margin here which is this one, and I'm saying that this is going to be right. So which is the better one? Let us say you have done these things when, or you have found out these margins and or W1s during
In
training, right?
Perceptron.
Yeah, but this happened during training, right?
Yes, sir.
Suppose any test data point comes in, and now the data point is here. What do you think about that? Okay, okay. First of all, I'll draw this line also, right? This is the blue line, and where is the red line? This one, right? It's like W2 transpose x equal to 0, right? And this is W1 uh, W1 transpose x equal to. Is that fine? So if this is a test data point, what the blue colored region will classify it as negative,
Blue colored region will classify it as -1.
negative, and this is the positive region, right? This is -1. What about the red colored one?
That will also classify it
Positive,
as negative.
Negative.
negative, right? Okay, fine. So now one more point I'll take, which is, let us say, a point here. This point. What is the classification of this point with respect to the blue colored line?
Minus negative.
Negative, right? And with respect to red,
Positive.
positive. So that means the chance that during test time, right? During the test, which one will be the better choice here? The blue one or the green one? Blue one or the red one?
Blue one.
Blue one, right? So what does it says to me? That it gives me the you know the accessibility for those, like whenever the any such kind of points will be there, it will still be able to classify it properly, right? And the blue one. So that means our margin, this gamma margin, should be
Large.
as high as possible, right? That is the so now we need to do some more modifications in the our previous algorithm. So what should we do now? We wanted to maximize what? Gamma, the margin, right? Right.
Yes, sir.
And what are the constants? Constant will be W transpose xi
Xi into yi greater
yi
than
should be greater than equal to gamma
gamma.
for all I. Is that the modification we needed? Right? We wanted to maximize that margin such that this is going to be this condition has to be satisfied, right? This is my objective function, and this is my constant. Is that fine? Now this looks
Yes.
good. Now this looks good, right? I'm fine. I think that part also we have found out. Like if I try to solve this problem, that means the solution I am getting and the solution you are getting, both will have the same solution. Is that correct? Because now whatever the let's say I have found out some W1, you have found out some W2, but still we will be getting the same, uh, right? Because then we will pick only that W which gives me the highest margin. Is that fine?
Yes, sir.
Right. But what is the problem with this also? And okay, what
There
is
are two. There are two parameters.
yeah, but the problem occurs when is, let's say, how large that gamma should be, right? So now, okay, yeah, that is true. Like if you have two parameters and you are just object, like this is the gamma thing, right? Let's say this is your partition and this is your gamma. So what does that mean? Do I have, and what is the equation of this line? W transpose x equal to 0. What is the equation of this line? W transpose x equal to
Gamma.
gamma. So if I so that means if I wanted to maximize gamma, so let us say is gamma is 2 gamma, right? So 2 gamma will be somewhere where, like it will be where it can be like some higher side, right? Or like that, right? And if I do that 2 gamma, then I'll have to multiply here also. That will give me 2 times the W. And what is the problem happening now? My
As you
W
increase the W, gamma will also increase.
increase, right? So what will be the solution we are getting? The gamma can
Infinity.
go
Infinity.
infinite, right? So then again that will not be the purpose, right? So, or either the gamma will go infinity, or it will go the uh, or your margin will be very high, right? So infinitely high. So then now that is the problem. So how that problem will be solved? And what we said again, we already said that this, what is the w should, what the w should be? Okay,
So you need this.
w is should satisfy this constraint. So if
Yes.
this is the constraint, then what will be, so if this w should be the that w which is satisfying this one, then my gamma, the feasible gamma with respect to this condition, so the solution to that problem will be what? Gamma equal to infinity, obviously, right? Because I'm not going to increase the w, I'm going to increase only gamma. So that will but that is not the good condition to have. So what we should do now, so basically we wanted this part, right? This width has to be as high as possible. Is that fine?
Yes, sir.
So if I get somehow this width, so width is basically it is 2 gamma, and I'll just say that width. So width should not be the function of gamma. The width should be the function of w. If I try to get that kind of formulation, then I'll be get rid of that gamma part, and I'll say that width is a function of w, right? Such that what, w transpose xi into yi should be greater than or
Greater
equal
than
to
equal
1
to.
for all I, and that is the problem we can solve. And the solution to that problem is what? Okay, that width is width of this function, right? It's coming out to be uh, the okay, width star w is 2 by, let's say, w star. Okay, uh, that is not solved here. Yeah, that is not solved here, but yeah, you can get it that part. uh, what does again that mean is, or okay, what problem we try to solve is, that is again we'll have to see. So where is the width here? So if let's say this was a w where it was constrained by, let's say that uh, that condition which is norm of 1 equals norm of square is equal to 1, in that case you have okay, sorry, this line will be what then? This 2 will be there, right? Suppose there is one data point here on this line. Okay, that data point is x, as we say, and whatever the data point here will be there, it is z, right? Okay, let us say z is the data point there. What is the equation, or okay, what is the equation of this line where x is there? W transpose
X
x
equal to -1.
Equal to.
okay, actually it should be gamma, but we are actually what, okay, one more step I think I have to tell you is that we can standardize this gamma, right? We can standardize this width to 1. So I'm just standardizing that gamma equal to 1. How to do that? Let's say W transpose x equal to gamma, right?
Bring
uh,
gamma to
yeah,
in
so
the
it will be W
denominator.
by gamma transpose x equal to 1. We can do that, fine. So this is that w which is standardized or scaled w, right? We can do that anyway. That is because gamma is a constant, and if I do that, then in that case, what is the equation of this line or this point? It is W transpose x equal to minus
1.
1, minus 1, right?
-1 for the left one and right.
Right. And what we are trying to minimize is now, or maximize this here, is this width, right? We wanted to maximize this width as far as possible. But again, in the other terms is what? The length of this should be,
Minimum.
you understand this
Dis-
part? Like,
Distance between the two parallel lines.
all of you understood this part? I don't know whether you guys.
The distance should be maximum or minimum.
It should be minimum. So it should be we wanted to find that z, right? That point which gives me the length as why, I'll tell you. Let us say you have okay. So generally, what is let's say your data set looks like this.
Sir, there should be minimum of xi and zi's now.
Not xi zi's. Okay, I'll tell you. Think these are the data points, right? Okay, I think I don't know where I missed to tell, but say this is w. Okay, this is a line which is, let's say,
Yeah, the closest you're saying also from both sides.
yeah. So these are called support vectors, right? But okay, let me. I'll just tell you. Sorry. So these are the data points. Fine. Okay. Now let's say this data point is on that line w transpose x equal to -1. Okay. Sorry. Sorry. The data point should be here, right? I'll just draw the line. This margin, right? I need to draw margin, and suppose this data point is here and other data points are here. Fine.
Yes.
I wanted, so margin will be what, like when we should whenever I get one of the data point which is actually on that line, or one or more than one. So right, we can have so many data points here, but the data point shouldn't be here, right, in this region, in this gamma region, right? The first data point which we can see, the other data point, if I'm able to classify it properly, whatever the data points remaining this side, they should definitely will be able to classify, right? Because this is the line we are looking for, right? Equal to gamma. Is that fine? Or minus gamma. Is that fine? That's okay.
Yes, sir.
Yes.
And we are saying that whatever the data points which are satisfying this condition, and that they will be on this side, we are saying that uh, okay, we are done, right? So then we are able to correctly classify all the data points there. Fine. So the important line for me is what? The w transpose x equal to minus gamma. Is that fine?
You
And
have
with
both
this
the lines w transpose x is equal to gamma or minus gamma.
one, right? -1. Fine. Okay.
Yes. Yes.
Now that means whatever the data points which are here on this line, they are the first ones which where we are actually able to correctly classify, right? Okay. Then from here, what I wanted to get is that, so okay, let's say if the data point is here, and let's say the positive data points also should be here. So which data point should I look? Like, should I look in the positive side, this one, or this one?
So closest to the decision.
Right? Because that should be the as close as possible, right? I cannot go for any data point, right? I hope you are agreed with that part.
Yes, right.
Yes, sir.
I
Yes, sir.
understand.
So whichever the closest one is there from this data point, that should be my uh, or that should actually give me that line, right? Exactly.
Sir, but how you will get that x point?
No, we don't need that X point. What I'm saying is, at least we should get that line, right? I understand the data point may be there or may not be there, but that if let us say in hypothetical condition, I'm saying that which of what data point should I look into? If I'm here, I should be looking the parallelly, right? Because we need anyway the distance from this line, right? This line. So if I am getting this gamma here, I should exactly able to get gamma on the other side also, right?
Yes, sir.
Sir,
Hmm.
our objective is still maximizing the margin gamma, no, sir?
Yeah, that is there, but in other words, what I'm trying to say is the length between this and this should be minimum, right?
Yes.
We are maximizing this width. Is that fine? We wanted to have, because okay, so let us say we had this width previously, suppose, right? This is a smaller width. I have some other widths, right, according to the W's, but I will choose only which width among all the widths. I'll choose the maximum one, right? Correct.
Yes.
But the
Correct.
maximum width also have that property which says whatever the data point here is there, the length of the closest data point I'll check, right, for this condition to satisfy.
Okay.
You're
Because
getting?
yes, the distance should be equal on both the sides.
both the
So
sides.
that's
Yes, yeah,
that's the reason we are trying to look for the point that is closest to the decision boundary.
right.
But our but our objective function is still maximizing the
Correct,
width.
correct. So that is right. Now let's say I'll try and give you the another picture. Suppose this was the, let's say, for one of the w's, this is going to be so let's say shall I not draw a w? That's fine for you. Okay, maybe I'll draw w1 is this, fine. This is the condition. Okay,
Yes.
this is going to be one of the widths, right? Width one, let's say. Okay, I'll draw another w, which is, let's say, this one. For this w, this is the going to be the condition, and let's say this is going to be w, right? So this is the width 2, right? And so we have so many things, right? So now which one I should choose? Width 1.
Yes,
Is that
Yes,
fine?
because it has largest margin.
Margin is larger. Now one other thing is, if I take one of the data points on this side, uh, that way can I have the positive data point here, or okay, can I have, okay, let's say if I try to get this, can I have this point, or can I have this point, or okay, which one should I prefer, or
The
in the
one
same
on
line?
the plane.
The
The one
closest
on the
book.
plane.
So what does that mean? Whenever I'm trying to maximize the width, at the same time what I'm trying to do is the length between this, the negative data side or and the positive one, should be
minimum.
minimum, right? So the same part I can write it like this, like either I can go for width w as maximum, right, where I will just do this part, uh, comma, or let's say 1 now, or minimize the distance between x, let's say, yeah, x is on the, x is the data point which is on the
Positive.
Negative side and
negative
Z
side,
is on the positive side.
negative side and the positive side, and such that w transpose z equal to +1. Is that fine?
Yes, sir.
This and this is the same, right? So I'm saying that now it is +1, w transpose z equal to +1, and here w transpose equal to -1. Here what we are saying, the constraints were different, right? W transpose xi yi is greater than or equal to 1. Now the same problem can be solved using this minimum of or trying to minimize the this distance, so that w transpose z equal to +1, right? So,
Maximize the minimum distance. That
yeah,
is
so
that.
see, this is correct, right? This is correct. So
Yes.
what are the data points which are qualified here? All these data points on the line. Okay, maybe I'll draw one more diagram for you. Okay, so let us say this is the w, which is actually giving me the maximum margin, right?
Okay,
Is it
sir.
okay? Now this is the maximum width we are getting. Now what does that mean? Let's say if I have one data point over here, this x data point, uh, I wanted, so let's say z is the data point on the positive side. So let's say this should be like, the equation should be w transpose z equal to +1, and the equation for here it will be w transpose x equal to
Minus.
Is that okay? So all the data points on this line, they will satisfy this condition, right?
Yes, sir.
Yes.
Right, all the data points on this line will satisfy that condition. So how many lengths I can get? Let's say this is one length, this is another length, this is another length, this is another length, like that, right? I'll get all lengths, right, from this data point. So which one I should prefer?
Minimum distance.
The closest one.
The minimum, and minimum will be this one, right?
So maximize the minimum distance. That is what.
But there is no
Maximize the-
maximization.
No
concept.
maximization. Now I'm saying that this is the case where I'm getting the solution, right?
Yes, sir.
Okay.
Got it, sir.
So this way we'll have to find it out, and the solution to this problem is this one. width of W. This is a separate condition. Okay, this is a different thing. So here it is, width of W is equal to what now?
2 by W square norm.
Right.
But sir, in one of the assignment, it was given the 2 by norm W, the width
This,
of
this is now
between
not
any
there.
hyperplanes. There is no square, sir. I mean, in this, in how
Long.
they solved it, yeah.
No, I don't think so. That should be. Okay, I think that will also be possible if you
Even
consider the
in the
one.
FAQs link, sir, they gave it as absolute value of C1 minus C2 divided by norm W is the distance between any two hyperplanes.
Hmm.
W transpose X equal to C1 and W transpose X equal to C2. So the
Okay, that
distance was
no,
yes,
I
sir.
don't think that is a problem, because anyway that is square distance and the square root of the distance, right? I It will not change much. Only because it's not going to change. Yeah, I don't think so. It will square if you try to minimize that also, or try to minimize or if you wanted to try to maximize also, it will not change. That's fine, not an issue.
And the distance between decision boundary and W transpose X equal to gamma is nothing but gamma by norm W, no, sir? The
Yeah,
geometric
but
mark.
what we are saying is gamma. We are removing that gamma and we are like substituting it by one, right?
Is setting it as 1. So 1 by
Ah,
norm W.
yeah. Basically, but the solution comes out to be 2 by norm W, or norm of W square, right? Okay.
Yes, sir.
So now we got this 2 by W gamma 2 by this now W square is from where? By solving this part, right? This part, fine. If you solve this condition, we get this width. Now we have got this width, right? Okay.
Yes.
Now the original problem was what? Maximizing this width.
Yes, sir.
Fine. Because we didn't know what is the width, right? We said that if I get this width in terms of W, I'll be happy. For that, what I did is we tried to take that X and Z and we tried to find out that solution. And that solution was this one, right? Now what is my objective again? Maximizing W for this. And what are the constraints? Such that W transpose Xi Yi is greater than or equal to 1.
Greater than or equal to 1.
This is the problem now I wanted to solve, right? Fine. And in the other words, what I can do is minimize W for
W square by 2.
by 2, and such that this will be the same y I greater than or equal to 1, right? Now these two are the same things. These are equivalents. I hope this is fine.
Yes, sir.
Okay, now I'll stop here. We can just continue from here tomorrow, and then I'll take the linear regression part. And I think all these things should be completed by maybe 1.5 hours, right? Right?
Yes.
But the distance between the distance between the two lines is 2, right? 2 divided by the norm of W, right?
W square. Yes.
Yes.
That this was a separate problem, right?
Yes. Yes.
Width we wanted to maximize. That is a different thing. But first of all, what I wanted to find that width in terms of W, right?
Yes.
When we started, we wanted to say that okay, this gamma is getting like any value. I don't want that, so I wanted this formulation I have done, right? Maximize W, so that I can satisfy the other constraint here. But what is this function? We don't know that, right? To get that
Yes.
function, what we said is we have taken one point on this part, and then okay, I need one another point on this part, right? W transpose X equal to +1. So that we wanted that minimum distance, and from to solve that problem separately, this problem separately solved, and the solution to that problem is what?
2 by W square.
And that is my width, because width of W is nothing but what? Distance of, right? Minimum distance. Is that correct?
Yes.
And now whatever so we said that the minimum distance between these 2 points, one point is on the negative side and one point on the positive side, this is coming out to be 2 by norm of w square, right? Now the next part is I wanted to maximize this width, which is that 2 by norm of w square, and now the constraints are there. Is that fine?
Yes, sir.
This problem now we
Uh,
wanted to solve. Yeah.
Sir, so the constraint that is given W transpose XY, we got it from the assumption one of Perceptron, right? Like the
Yeah,
linear
yeah, yeah,
separate.
yeah, yeah, yeah. All the things we have gone through, like the same. We wanted to connect it back again. Why
Okay.
we were not able to correctly identify there? You what we found out some problem, right? Some issue there.
Yes,
Then I,
sir. Yes.
then we with the linear separability condition also we were not able to say that which point
But
should
the
I look at.
optimal
Yeah.
W. Yeah.
Or should I go for all the data points or should I go for some more data points? So we actually gone for the some data points, right? Which are these
Yes.
support vectors. So we don't need actually all these points, right? All these points, this
Yes. We
side, this
only
side,
need the points that are on the
hyperplane,
pattern. Okay.
hyperplane to margin, right?
And not
Uh,
all of them also. Not all of them also.
Yeah, not all of them also, but yeah, that doesn't matter anyway. That like we wanted those lines to be, and we wanted that distance has to be minimum between that, and we wanted that width to be maximized. That is my problem, right?
So,
Okay.
sir, the constraint greater than or 1, it'll be equal to the left side also as well, no, sir? W transpose Xi into
Yeah,
Yi
this is
is great.
this
Yeah.
this we said no, because this y can take plus and minus sign, right? If I
Yes, yes.
multiplied,
So it will change accordingly for
yeah, yeah.
the
So
left side.
basic
W
constraint was
transpose Xi Y will always be positive.
we said no. This is this to be
If it
condition to
is
be
negative,
satisfied
then it is incorrectly
greater than
classified.
1 and w transpose x is less than or equal to minus 1, right? This
Yes,
was
sir.
this is what we wanted, but if I just multiply with y, I don't need two conditions. I just need only one condition.
One condition.
Why?
Okay.
Because you just see that w transpose x is less than or equal to minus 1. This is possible only for positive class. This is for negative class, right?
Negative class. Yes.
So negative positive class means y equal to plus 1. So if I just multiply
Hmm.
here 1, I'll get that condition. And this is y equal to minus 1. If I multiply with this minus 1, so what will happen? W transpose x is greater than or equal to 1.
Greater than or equal to 1.
So
Okay, okay.
basically, I don't want these two conditions separately. What I'm doing is I'm just multiplying with yi. Now I will get that this condition.
Okay, sir. Got it.
Okay.
Thank you.
Yeah. Both are the things. Both things are actually so this one constant I getting me both the conditions.
Okay. Greater than or equal to 1, less than or equal to minus 1.
Yeah. Because that depends on the label y, right?
Label Y, which will be plus and minus. So we're just ensuring that it'll be beyond the margin gamma equal to 1.
Hmm.
It should not lie before the gamma margin.
Right.
Thank you, sir.
Okay. Done. So whatever left is there, we'll do it tomorrow. I don't know what is the timing. Maybe 11:30 will be fine. I
Yes,
hope.
sir.
Huh? Okay, I'll
Yes,
schedule
sir.
that today to 11:30 tomorrow morning. Maybe we'll finish it by 1:15. Or whatever, if it is remaining, maybe Nikita will cover in Friday session.
Thank you,
Sir,
sir.
can you share this PDF, sir?
You need it. Okay, I don't. Okay, I'll share that. I will attach it to the today's session. Okay.
Okay, sir. Don't forget, sir.
No, no, no.
Please.
I think last time also I have done it, right? I have
I
attached
don't
it.
know, sir.
Yeah, I have attached
Last
it
time
last session
I
also. I have
saw notes, it was updated till like week 5.
No, no. Check in the calendar. The session I have attached. It is not in the
Uh,
supplementary content.
it'll be in the link
Calendar.
again. If
Yeah.
yeah.
Okay. Okay, guys. Thank you. Bye bye.
Thank you, sir.
Thank you, sir.
Bye.
Thank you.